Welcome back to Basic Electronics. In this lecture, we will continue with the input bias current of an op-amp and look at its effect on inverting and non-inverting amplifiers and also on the integrator. Next, we will start with a new topic, namely op-amp filters. To begin with, we will see what is meant by a filter, what are the various types of filters, and how to represent a filter with a transfer function. Okay, let us begin. Let us consider the effect of bias currents on the inverting amplifier now. So we replace the op-amp with the real op-amp model, which includes the bias currents. And now let us see what VO should be in this case. We will assume that the op-amp is ideal in other respects. That means we will say that the offset voltage is 0 volts. We have already considered the effect of the offset voltage on the inverting amplifier, and we will not repeat that here. So to begin with, since this is the ideal op-amp, V plus and V minus are the same. V plus is 0 and therefore V minus is also 0. And if V minus is 0, this current I1 is Vi minus 0 divided by R1, that is Vi by R1. Now I2 is not equal to I1 in this case because we have IB minus going there. This current is still 0 because that's an input current for this ideal op-amp. So therefore I2 is I1 minus IB minus, that equation. And now we can write an equation for VO. VO is V minus, which is 0, minus I2 times R2. And we already know I2. It is I1 minus IB minus. I1 is Vi by R1. So we put it all together and then we get minus R2 by R1 times Vi plus IB minus times R2. The first term, minus R2 by R1 times Vi, is simply the output voltage we expect from the inverting amplifier. And the second term arises because of the bias currents. Now IB minus is a constant, R2 is a constant, so therefore this term represents a DC shift in the output voltage. Let us see how large it is. Take an example. IB minus equal to 80 nanoamperes, R2 equal to 10K. So IB minus times R2 is 80 times 10, 800. Nano times kilo, that is micro. So we have 800 microvolts, the same as 0.8 millivolts. So that is the DC shift we will expect in the output voltage in this example. Let us now look at the effect of bias currents on a non-inverting amplifier. To begin with, we replace the op-amp with this model, which includes the bias currents. And we will assume that the op-amp is ideal in other respects, including VOS equal to 0. Now since this op-amp is ideal, V minus and V plus are equal. V plus is equal to Vi, the input voltage, therefore V minus is also equal to Vi. And the current I1 therefore is 0 minus Vi divided by R1, that is minus Vi by R1. This current I2 is I1 minus IB minus because this current is 0, that's an input current for the ideal op-amp, and therefore we get I2 equal to minus Vi by R1 minus IB minus. And now we can write VO as V minus minus this voltage drop, which is I2 times R2, substitute for I2 from there, and we finally arrive at Vi times 1 plus R2 by R1 plus Ib minus times R2. Now this part is the output voltage we expect from a non-inverting amplifier, and this is the effect of the bias currents. Now Ib minus is a constant, R2 is a constant, so therefore this term is simply a constant or DC shift in the output voltage. Next, let us look at the integrator and see how it is affected by the bias currents. First, we replace the op amp with this model, which includes the bias currents. Let us look at the output voltage with the condition that Vi is 0. So this is 0 volts. Now this is an ideal op amp with V plus equal to 0. So therefore V minus is also equal to 0. Now this resistor has got this node at 0, this node also at 0. So therefore I1 would be 0. And I2 then would be equal to minus Ib minus. In other words, a constant current will now flow through the capacitor, and that will drive the op amp into saturation. That is a situation we definitely don't want. What is the remedy for this situation? The same as what we saw for the offset voltage problem, and that is to connect a resistor R prime across the capacitor, and that provides a DC path, so the current would now flow like that, and the output voltage will now be V minus, which is 0, plus this voltage drop, which is Ib minus times R prime. So our VO will now have a shift equal to Ib minus times R prime, and the op amp will not go into saturation. As we have discussed earlier, R prime should be small enough to have a negligible effect on VO. That means we want this delta VO to be small. At the same time, R prime must be large enough to ensure that the circuit will still function as an integrator. And we have commented on this point when we were discussing offset voltage and its effect on the integrator. Let us now see how the inverting amplifier circuit can be modified to reduce the effect of the bias currents. And if we recall, what is the effect of bias currents on the inverting amplifier? It was to cause a shift, a DC shift in the output voltage. So the modification we consider is adding a resistance R3 here between the non-inverting input and ground. And let us see how that affects the output voltage. So first we replace the op amp with this model, which includes the bias currents. And now let us analyze this circuit. And notice that since we are interested only in the effect of bias currents on the output voltage, we have deactivated Vi. That means we have connected this node to ground here. So we will analyze this circuit with that condition. Let us start with V plus. This current is 0 because that's the input current for the ideal op amp. So therefore this Ib plus would go like that, and the voltage at this node therefore is minus Ib plus times R3. And since this op amp is ideal, V minus and V plus are the same, therefore V minus is also equal to minus Ib plus times R3. And now we can get this current, V minus divided by R1. So I1 turns out to be minus Ib plus times R3 divided by R1. What about I2? I2 is I1 plus IB minus. And now we can write an expression for VO. VO is V minus plus this voltage drop. So that is what we have here, V minus plus I2 R2. We already know V minus from there. I2 is I1, which is this quantity, plus IB minus. So all that can be written as this expression here, minus 1 plus R2 by R1 times IB plus times R3 plus IB minus times R2. Let us now rewrite this expression for VO in terms of IB, which is IB plus IB minus by 2. We have seen this definition earlier. That is the average of these two currents. And IOS, which is the offset bias current, which is the difference between IB plus and IB minus. And from these equations, we obtain IB plus as IB plus IOS by 2 and IB minus as IB minus IOS by 2. Now we can substitute these expressions here, and then we get all of that, which can be rewritten in this form. Now in this equation, we have this 1 plus R2 by R1 outside the curly brackets, and within the brackets we have two terms, one involving IB and the other involving IOS by 2. And now what we can do is to take advantage of this minus sign here, choose R3 to be equal to R1 parallel R2, in which case this entire first term will vanish, and that will surely lead to a much smaller output voltage. Let us see what that is. So with that substitution, R3 equal to R1 parallel R2 over here as well as over here, we can simplify this VO further, and that turns out to be minus R2 times IOS. And if you recall, IOS is the offset current, and that is much smaller than IB, and therefore this voltage is a smaller DC shift as compared to R2 times IB minus, which we obtained when R3 was 0 or R3 was not connected. We had connected directly the non-inverting input to the ground. So this is one trick that you will often see implemented in op-amp circuits, especially when the DC shift at the output is a concern. So we have looked at the effect of the offset voltage and also the bias currents on several circuits: inverting amplifier, non-inverting amplifier, and the integrator. And the question that arises is it really a matter of concern? Should we worry about it at all? Let us look at that question. For the integrator, we have seen that VOS and IB will lead to saturation, and that of course is disastrous, and that has to be corrected. And how did we correct that? We provided a DC path, a resistor in parallel with the capacitor, and that solved this problem. So that only gave us a DC shift and did not cause the op-amp to go into saturation. What about the inverting and non-inverting amplifiers? It depends on the application. Let us see in what way. In AC applications, where the signals are varying with time, for example audio signals, the DC shift arising due to the offset voltage or the bias current is really of no consequence, because in such circuits there will be coupling capacitors to couple the various stages, and these coupling capacitors will just block that DC shift delta VO. So that DC shift really will not have any effect on the output. So in these situations, we really don't need to worry about the effect of the offset voltage or the bias currents. A DC shift is a matter of concern when the output is expected to be DC or slowly varying. For example, consider a temperature sensor. So we have something like a bridge circuit to sense the temperature that gets amplified maybe in one or two stages and finally displayed or supplied to some control circuitry. Now in these situations, a DC shift is definitely a matter of concern, which arises because of VOS and IB, because that is going to lead to a wrong temperature value being interpreted. So in these situations, definitely we must worry about the offset voltage as well as the bias currents, and we should try to minimize the effect either by choosing an op amp which has much better values of these parameters or by using some circuit tricks. Let us now talk about filters, a very important class of electronic circuits, and they find applications in many different areas. What we will do is first look at what a filter does, what its functionality is, and then we will see how it can be implemented. Alright, so let's take this simple example where we have V of t as a sum of two components, V1 and V2. Each of them is a sinusoid. V1 is Vm1 sine omega 1t. V2 is Vm2 sine omega 2t. This is our V1. It has a lower frequency. And this is our V2. So V of t, which is the sum of these two waveforms, looks like this. And now what we want to do is to pass this resulting waveform through a filter and see what we get at the output of the filter. Now let us look at the action of a low pass filter on this waveform. And before we do that, let us look at the transfer function of a low pass filter. That means the ratio of the output to the input of the low pass filter. And that is given by this graph here. This is the transfer function of the low pass filter. This axis is the angular frequency in radians per second. If omega is less than this cutoff frequency, omega c, then the transfer function is 1. That means the low pass filter passes all frequencies up to this frequency. If omega is greater than omega c, then the transfer function is 0. That means the low pass filter rejects or blocks frequencies higher than omega c. Now our input voltage is composed of two frequencies, this low frequency and this high frequency. And if we choose the cutoff frequency of the low pass filter to be somewhere in between these two frequencies, then what will happen is this high frequency component will get rejected and only the low frequency component will get passed, and therefore at the output we will have VO equal to V1, that is the low frequency component. For a high pass filter, the situation is exactly the opposite. For omega greater than omega c, the transfer function is 1 and therefore these frequencies will get passed. For omega less than omega c, the transfer function is 0 and therefore these low frequencies will get rejected. Okay, so let us see what happens when this same input voltage is now applied to a high pass filter. And let us say that we choose the cutoff frequency of the high pass filter to be between these two frequencies. Then what happens is the high frequency gets passed and the low frequency gets rejected. And therefore at the output of the high pass filter we have VO equal to V2, that is the high frequency component. Alright. Now there are some other types of filters as well, and we will be looking at these very soon. Let us now look at how a low pass filter is represented. In particular, we will look at an ideal low pass filter first. The transfer function of an ideal low pass filter looks like this. H of j omega is 1 up to omega c, and beyond that it is 0. And the output of the filter is given by, in the frequency domain, h of j omega times vi of j omega. Here is an example. Let's say our input voltage has various frequency components or Fourier components, 1, 2, 3, 4 components, and these components will have different values or amplitudes. Now if we pass this through a low pass filter with a cutoff frequency omega c located here, then it will pass these two components but block these two, because these two will get multiplied by 0, these two will get multiplied by 1. So our resulting output in the frequency domain will look like this, where the high frequency components have been eliminated. So all components with omega less than omega c appear at the output without attenuation, and all components with omega greater than omega c get eliminated. And how do we express mathematically this h of j omega for this ideal low pass filter? It is simply 1 for frequencies up to omega c, and that 1 is the real number 1, so we can write that as 1 plus j0. An ideal high pass filter does just the opposite. So its h of j omega is 1 for all frequencies higher than omega c, and it's 0 for all frequencies which are lower than omega c. So it passes high frequencies, that's why it's called high pass, and blocks low frequencies. Here is a filter called the band pass filter. So it passes a band of frequencies between omega L and omega H. So between these two frequencies, its value is 1, and otherwise it is 0. Here is a band reject filter. In other words, it rejects all frequencies which are in a specific band given by omega L and omega H. So its transfer function is 0 in this band and it is 1 otherwise. Note that all of these are ideal filters. In real life, we would not be able to implement filters with exactly these transfer functions. So we can approximate these transfer functions with certain mathematical expressions and then realize those with circuits. Let us now look at the effect of ideal filters on a sample waveform. The waveform that we consider is this V of t. It has three frequency components, V1, V2 and V3. V1 has a frequency of 0.1 kilohertz and an amplitude of 1. V2 has a frequency of 0.5 kilohertz and an amplitude of 0.2, and V3 has a frequency of 2 kilohertz and an amplitude of 0.1. So we are passing V of t through our low pass filter to start with, which has a transfer function given by this plot here, and the cutoff frequency of that filter is 0.4 kilohertz. So all frequencies up to 0.4 kilohertz will get passed and all higher frequencies will get blocked. So what happens? This component gets multiplied by 1, these get multiplied by 0, and therefore only this one survives, and therefore we see V1 of t at the output of the filter. as shown here. If we pass the same v of t through a high pass filter now with this transfer function here, then only the high frequency component survives. These two get eliminated, and then at the output we have the voltage corresponding to this component, that is V3 as shown here. What about a band pass filter? Here is an example. So the transfer function is 1 here between these two frequencies, and it is 0 otherwise. Now only this component which lies in this band will go through, and these two will get eliminated, and therefore we have the green one, that is V2 of t as shown here. Similarly, if we pass V of t through a band reject filter which has a transfer function shown here, then this component gets eliminated. This low frequency component and this high frequency component go through, and what we get at the output is a combination of this V1 and V3, and that looks like this. To summarize, we have completed our discussion on input bias currents of an op-amp and started a new topic, namely op-amp filters. We have looked at how a filter can be represented with a transfer function h of j omega. In the next class, we will look at the use of Bode plots to show how a given transfer function varies with frequency. That is all for now. See you next time.